Okay, great. So you guys can see my screen, right? Okay, great. So what I've done is I've implemented the boosting algorithm on the Boston dataset, and we'll see how it has, improved the performance of the algorithm. I mean, prediction, what we were trying to do yesterday. Okay, so let's start. So these are the packages that I import. So this is the same Boston data set. Here, what I do is I kind of take a subset of zero point 0.9. I mean 90% I take for training, and the rest 10% I take for testing. Okay, so this is a simple subsetting procedure. Okay, then what I do is I take the parameters of the boosting. So n estimators, n estimators is the number of trees that we want to build. Max depth we also know. Minimum sample split you also know. I mean, how many number of samples should be there in a node so as to go ahead with the splitting. Okay. Now this is called learning rate. There's something very important which is learning rate in boosting. The learning rate, as you know, that boosting is a series learning, right? So one tree will falter, and the next tree will try to improve on the previous tree, and then so you understand, right? So this is a series learning. So learning rate is basically how fast you want to reduce that error. So uh, points. So, for example, if you guys remember stochastic gradient descent, the example that I gave you on the second day or the third day when we started linear regression, the bowl example, the water droplet, and we were saying the water droplet will jump from one place to the other place to go to the minimum bottom point, right? So the bottom point is the minimum most point. So if you remember, there was a learning rate there also. We were saying that depending on the direction. So with the slope, I was able to find the direction, and then with the learning rate, I was able to give it the number of steps you want to go. So if it is too fast, if you want to achieve your lowest value too fast, you will never achieve because of the oscillating movement. If you don't remember, don't worry. I'll later when I switch to the iPad, I'll show you what I was meaning here. But learning rate is basically how fast you want to go to your minimum. Okay, if it is too fast, you'll never achieve. If it is slow, if it's too slow, then also you'll never achieve. Okay, so I'll show you. Just remind me this when I go to my iPad. So loss is LS. It doesn't. This doesn't make much sense here. So CLF ensemble gradient boosting regressor. This is the model what you are trying to. So gradient boost is the and the regressor. So we're doing a regression problem. So that's why I put gradient boosting regressor. Okay. Now so CLF.fit, I fit on the training data, and then we use the test data. So I fit the model on the training data, then use the test data to predict and see what it is vis-a-vis the actuals. So then I print the MSE, mean square error. Now, so I've just used some plotting. So this part is basically I want to see how. So this is called the stage predict. Okay, so at every stage of parameters, it is kind of giving you a curve that with increasing number of trees, how your model strain error and test error will change. Okay, so and this is the all the properties of the plot. So nothing special here, just the title, how what we want to see. So NP A range. A range, if you remember, is starting from the zero to the. So for example, N estimators is 500, right? So 0 to 49, not 0, 1 to 499, it will start. Plus 1 because I want 500 here. You remember Python always starts from, I think it is from 0. So 0, so that's why I have 1. here and 499. That's why I have 1 here. Okay, so it kind of it travels from 0 to 499, plus 1 makes it travel from 1 to 500. Okay, and this is the blue line, this is the red line. The location where you want to put the legends, it's on the upper right. What should be the labeling of X and what should be the label of Y. So if you run this, now uh, boosting also gives you a feature importance plot. So yesterday when someone asked me, I think Sunil was asking that uh, though we have in Baruta plot, it will give you rank, and what if I want to see top 5? So in random forest, I said that it is not possible, right? Because it is giving you the ranks of it. And if you want to go by the ranks, it is, I mean, you cannot find top 5 from the ranks, but boosting will improve further and will give you the top 5 variables of the rank. So these are all just to plot that. Okay, now see here, the interesting part. So your MSC is 6.6629. I'll show you what is it in terms of accuracy. If you remember the R square that we were talking about, we'll see that. But first see this. So this is your training error, the blue one, and this is with the testing error. So I've already always talked that with the increasing number of trees, your training error will decrease, right? And your testing error will decrease, but at a certain point of time, it will start to increase. We haven't reached that point yet here, but you see how your testing error and training error is behaving. Okay, and this is your variable importance plot. So you see which all variables are important according to their this is relative importance. So according to their importance, they are being ranked here. So if you want to take top 5 variables here, you can take it from here. Okay, now uh, yeah, thanks, Sunil. Not a problem. That's why I always say go step by step. You will get all of whatever you want to um, learn. I'll tell you, but just have a little patience so that we proceed step by step. So now see the formula that we learned yesterday. What was it? One minus standard deviation. Sorry, one minus RMSE. Vasant says how LStat. LStat. Okay, what was LStat? I need to check. I mean, I need to check what was LStat. We'll address your question, Vasant. Just wait. Let me complete this. So if you see that the formula that we're trying to do is 1 minus the mean square error divided by the variance of the data. Now see, you have achieved 88.19% accuracy, which was previously what 50% max to max, and that too I have not even optimized my algorithm. Just a simple random estimators and learning rate and the minimum and max step randomly I have achieved 88.19. And if you even do a grid search or a very good, try to tune the model, you'd even go up to I think 92, 93%. So that's the power of boosting, how it improves the algorithm from a simple random forest. And it's not difficult to implement, it's very easy. So you see how your accuracies have improved drastically. Now, Sunil, Vasant had this question: what is LStat? Just a second, I need to see what is LStat. So, uh, let me see. Percentage of lower status of the population. So, I think this is this actually makes sense, right? If your population is having a lower status, I mean, it means that neighborhood is not very expensive, right? That's why the prices of that neighborhood will be very low, right? So I think what it means is, like, let's say if it is 30% of the people are the lower status in that neighborhood, then of course that neighborhood is not very posh, and that's why the prices of the house will be uh, low. Or if the percentage of lower status of the population is less, then it means the neighborhood is very posh, and it will be very I mean, it will be very posh. So does this answer your question? And you see the second variable, if we can see here, RM is the second most important. RM is the second most important. So if you go to RM, where is RM? Average number of rooms per dwelling, of course. So if your number of rooms is less, then obviously your price of the house will be lower. If the room number of rooms is high, then the price of the. So basically, what your algorithms will tell you regarding these variables is that what is the variation of this particular variable vis-a-vis the price. So if your LSTAT, when varying from low to high, is it really changing the price from low to high? And if it is yes, it means yeah, it is a very important variable. Kind of if there is a good amount of correlation. Okay, so I think this helps a lot, I guess, to understand the differences between the algorithms. Okay. So any questions now? I'll just, everyone is unmuted, I think. Anyone can ask me any questions so that we can close this chapter of bagging and boosting and then move on.
Yeah, this is Krishna here. Can you go a little up?
Yeah, sure.
So you had that 80% this thing, right?
90% division, right?
Yeah, that after the graph you had that this thing, right? The code.
The
Still up.
even up, I think this is the code only. Which?
Oh no, I think after the graph you had the NumPy, standard deviation, all that, right?
Okay. Yeah.
Yeah. So what is 1 minus 6.6? What is that value coming from?
Okay. So what I did is I just manually calculate 6.6 is this one. So the mean square error, what we
Oh,
learn is the yesterday I told you, right? 1 minus mean square. So we are taking R square. R square means
okay.
squared of distances. So 1 minus MSE is the what your model has able to after fitting. This is what is left, and your 55 is the 55 point is this is basically B only. So B I calculate, I just put manually the value. Yeah, so B is basically the standard deviation, the variance or the naive estimate as a mean. What is the average error when you put the mean? So on that basis, we learned right last class at the end, R square is equal to 1 minus MSE upon standard deviation. I mean variance. Now because we are talking about R square. Okay, so this is 88.
No, because the number, I didn't know the number. That's what I was thinking.
Okay, no problem. Sorry, that's my fault actually. I should have.
No, that's okay.
Yeah. So perfect. That's what I just wanted to. So you see how your R square has changed drastically, right? We were seeing somewhere around 0.48 and something. Now it is 0.88. So that's why people who are machine learning, who are doing machine learning, so they start with boosting because they know that the other. So why it is important to learn these linear regression, lasso ridge, random forest. So boosting is basically a combination of random forest and boosting as a process. Okay, so gradient boost is not an independent thing. So if you don't understand random forest, then you will not be able to understand boosting. So if I say just what these are the number of trees, what are they doing? So if you don't understand random forest, you will not appreciate what boosting does. Better than it. If you don't understand linear regression, you'll not understand how random forest is. You'll not appreciate how random forest is improving the model. So that's why it's very important for. But having said that, if your God's function is linear, right? If your God's function is linear and you fit boosting, it will be worse than what a linear regression can fit. That's why when you never know what is the nature of the function that you're dealing with, it's always better to start with a simple model and then move on to, because you never know which is the actual function, and there's no particular answer to any defined answer to any question that this is your model which will work the best. You just have to try and gain your experience. Okay, so are we comfortable with bagging and boosting so that we can move on to the next part?
Yeah, I have one question, last question, sorry.
Yeah, sure.
In the boosting, right, the values which are not calculated from T1 goes to T2, right?
Correct, correct.
So let us say, and uh, the futures in each T1, T2, T3, all are different, right?
Yeah, 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 yeah.
Or it will be the same future. It will take all the same future, the
No, no,
same order, or it
no,
will
no.
take different futures.
No, no, different. So I that's why I said, right, the random boosting is a process that is being added to the random forest itself. So what was random forest doing? It was dealing with T1 P1, T2 P2, T3 P3. I mean, even different sets of data. But in boosting, it is the same thing, just to ensure that when your second data set is picked up, right, you make sure that the previous data points which were not classified or which had a very bad RMSE in terms of regression, they are taken by the T2, right? With
Oh,
different number, different predictors. It can be different predictors. It should be different predictors, right? Otherwise, every a tree tries to fit with the same predictor, they'll always fail in predicting that certain amount of data, right? So that's why you have different
so
predictors.
yeah, in that case, what you're saying is, okay, this particular data set, which is not fitting for this particular future. So I'm going to try another set of future. That's
Correct,
what you're
correct,
trying to
correct,
do, right?
correct, correct.
Okay.
Yeah.
Okay. Thank you.
Okay. So any other questions? Anyone wants to ask? I mean, then we'll move because SVM is not related to any of this. So SVM will be a completely new, different model. So that's why I was asking. Okay, so then I'll move on. If everyone's okay, so I'll just um, just bear with me for 2 minutes. I think. Uh, okay. I think we are good here. Okay, so we start with a new topic called support vector machine, and it's a little difficult to understand this topic, and it has a lot of mathematics. But I'll not go too deep into the mathematics part since it's not, frankly, it's not required to go into so much depth. But you just need to understand how support vector machine works. And in certain cases, it does prove to be a very good model, and that's why you should not ignore this, because there are certain cases where you may find that your boosting is not performing very well. Then you might have to go with the support vector machine. But there's a lot of advantages to this model as well as disadvantages, so we'll talk each of them. So uh, so basically, it's kind of a, first we'll talk about a linear classifier. Okay, so what it does is, it says if my data is like, it's somewhere here and the other classes is here, okay, why don't you have a boundary between these two data sets? Okay, so good enough, right? But I can say, why this boundary? Why not this one? There are actually infinite boundaries that you can have here, right? So let me talk about first thing is like, what is a hyperplane? So you might have hear about this hyperplane concept a lot of times when you go into support vector machines. Don't get confused too much. In a two-dimensional space, a line is a hyperplane. In a three-dimensional space, a plane is a hyperplane. In a four-dimensional space, a three-dimensional plane is a hyperplane. So for after four dimensions, you cannot, after three dimensions, you cannot visualize, right? So we'll not go into depth. So whatever your let's say whatever your dimensions are. So for example, let's talk in terms of variables. If there are three variables, okay, equation of uh, this is called a two-dimensional hyperplane. Why two-dimensional? Because it involves two variables. So in a three-variable space, you can have a two-dimensional hyperplane. So, for example, if there are three variables, x1, x2, and y you want to predict, so a hyperplane that is that is having x1 and x2 in the equation. So let's say b naught plus b1 x1 plus b2 x2 is equal to y. Okay, so this is your hyperplane. Okay, so I always remember, in a three dimension, whatever dimension variables you have, let's say if you have multiple variables x3 x4, so if you have four variables, I mean including y, if you have five variables, then a four dimensional hyperplane is a boundary. Okay, so let's rub this. I how to Okay, yeah, I got it. So basically, this is what you are trying to do: fit a boundary which linearly separates the boundary. Now, as I said, there can be infinite boundaries, right? One boundary can be, let's see, this one boundary can be this. So, which boundary should you choose, right? No one has told you which boundary you should choose. So, what you do is you choose a boundary which is farthest from here and farthest from here. Okay, so you choose a boundary which is kind of separating the data best. I mean, so what if a line which is farthest from here, and the same line should be farthest from here, but these are two opposing directions, right? It means you want to fit a line which is kind of a middle space in between these 2 points, right? If you get that line, that is your support. So these are called support vectors. Why support vectors? Because they're kind of supporting the line from both the sides. Okay. It's not working. I don't know why I cannot choose a different pen. Anyways, so you get the point, right? So for example, if I redraw, so this is the line which is kind of max distance from this point and max distance from this point. Okay, so have you understood this part? First of all, tell me. I'm open to questions right now. Have you understood this part?
So why we are choosing these specific points? Is there any reason?
So right now, because your data is linearly separable. Why I didn't choose this line? Because it is not separating the bound two classes properly, right? It is, let's say, if the left side of the boundary is black, the right side of the boundary is white plus black. Okay, so you kind of try to create a boundary so that the left side of the line or the plane is one class and the right side of the plane or the line is one class. Do you understand? You want to, so that what you can say, so in equation terms, let's say this part. So if the equation of this line, or let's say if the equation of this plane is b naught plus b1 x1 plus b2 x2, if you say my new test data comes and I find out the value on this, if it is greater than 0, then I classify this as the positive class, or let's say this is a positive class and this is the negative class. If my new data, I put this data in this equation and I found out that the value is b naught plus b1 x1 plus b2 x2 is less than 0, then I classify this as a negative. Okay, so what I'm trying to do is we are trying to classify the data set in terms of where it positions itself. The point is positioned with respect to the line. So if it is on the left side of the line, let's say it is greater than 0, and if it is on right side of the line, it is less than 0. Okay, does that answer your question?
Oh, yeah, kind of. So what do you mean by max distance? The line is max distance from that point. What do you mean by that?
Okay.
You are drawing this straight line, which you are showing right now.
Correct.
So max distance will not be. Are you trying to optimize between these 2 points?
So if
that it need to be max distance from this point as well as this point. Is that what you mean?
Okay. So let's say if I ask you to draw a line to separate these points. I mean, the left side and the right side, the black points and the dotted points. What would you be doing? You'll draw a line, right?
Yeah.
Yeah. But which line? There can be infinite lines between those 2 points, right? There can be a line which is very, let's say, if I even draw a line like this, it will still separate the blacks on the left and the whites on the right. If I draw a line like this, I can still separate the right points, and this is much easy. I mean, this is even a little difficult to visualize. Let's say you have like this, and you have something like, let's say these. How many lines you can fit? Many lines you can fit, right? Which separate
infinite, yeah.
Infinite lines. So you need to have a measure, right? Which is the best line you want to fit. So what it does is it says, okay, tell me the closest point from, let's say I want to fit a line between this. Tell me the points which are closest to this line. So let's say these are the points which are closest to this line, and I want to maximize this distance so that it kind of lies in the middle of these 2 points. Does that help?
Okay. Yeah, got it. So you're trying kind of like drawing a perpendicular from that particular point
Correct.
To this line. So that way your line is defined. Okay.
Correct.
Makes sense.
Yeah. So it's kind of what we did in linear regression. What we were doing, we were having like these points, right? And then we draw a line. So what we were doing that these distance should be least, right? This error should be least. Here, what we are doing is that it should be maximum. I mean, it should be well separated here and well separated here. I don't want this to be too close here, or I don't want this to be close here. Everyone gets this. This is the basic of SVM. Okay. I don't know why I'm not able to change the lines. Anyways, so just a sec, it will show up. Yeah. So basically, this is what I was referring to. Let's say your black points are positive, and your the white points are negative. Okay. So this is how you wanna separate the line, separate the data. Okay. So you see, there can be infinite lines, right? But which is the best one? So you kind of have a kind of line which is define the margin of a linear classifier as the width that the boundary could be increased by before hitting a data point. So whatever I said, that's written in English, right? Whatever. So kind of you want to have the highest possible margins of that line in the data set. Okay. So why it is called maximum margin classifier? So we are increasing these margins. These are the margins. We are trying to increase these margins to the maximum. This is the simplest kind of SVM called LSVM. Why linear SVM? Because we are fitting just a line. We are not doing anything. We're just fitting a line. These are called the support vectors because these are the points on which your point, on your data lies. Now, can anyone tell me what is the major disadvantage of this? I mean, uh, just to this point, whatever we have done, what is the major disadvantage?
So if there are any exception on the other side, the line will not take care, right? Because right now your data is what you are showing on the screen is pretty separated, but there might be anomaly, right? Some dotted point might be on this side and the other side.
Very good. That is a very big disadvantage, that everything is not linearly separable, right? Right now you visualize that your data is linearly separable. Okay, I can draw a line, but many times you cannot have a data which is linearly separable, right? There will be a mix and match of it both. So that is very good. That is a very good disadvantage. I mean, very big disadvantage of linear SVM. One more thing is a very big disadvantage of SVM. Okay, I'll take. You see,
Yeah, it might be the point, the lowermost point, right? Say the upper portion cluster, the point is too high, and the lowermost is too near. Then you might have a different fit or something like that.
Not precisely that, but the problem is that the model you see doesn't take care of all these points. I mean, it doesn't even bother those. It's only dependent on 2 points which you're trying to fit the model from, right? So only the 2 support vectors are kind of determining the model. What about all these points, right? These are not even taken into consideration. So why I want to fit a model which is just dependent on 2 points? So this is a very big disadvantage of SVM. I mean, it's like uh, I mean, you have so much of data, and then you're just using 2 points to fit your data. So that's kind of a big thing that you don't want to have as a modeler, right? But similarly, what plays in its favor is when you have too less data. So SVMs perform very good. So if you have too less data in boosting and random forest, you you are taking let's say subsets there. You're taking back when you're doing bagging and boosting. You're taking subsets of data. So if you have just 20 or 30 data points or 100 data points, your subsets will start repeating after a certain point of time, right? So that's why when you have uh, too little data, SVMs perform very good, precisely because of this point, because they don't want to look too much of data. They just fit using these two. But having said that, it doesn't mean that the SVM will perform very bad in bigger forms of data. But it is not very. I mean, it's very powerful. Sometimes it gives very good results, but sometimes it performs very badly. So SVM is something like it's it's kind of a hit and trial. You may end up with a good result, and you may end up with a bad result. But you remember in one of the classes I told, if there is a circular data, your forests and decision trees and linear regression will fail. This is where your SVM will shine. So right now you don't understand because we have just fit a linear SVM. Now there can be multiple forms of this partition. So what we'll do, let me go to OneNote and show you. So for example, if you're let's say your data is circular, okay. So what SVM, so SVM is known for something called kernels. Okay, so what are kernels basically? So like what we just saw was a linear kernel. Okay, so linear kind of a line which is trying to separate. Can have a circular kernel. I can have so circular is a two-dimensional. Uh, I mean, let's say you have a circular partition. Okay, so you can have a polynomial kernel. Okay, so you can have any type of kernel you can imagine. So what it does is, in two-dimensional, this thing is looking like that they are circular, but if you add another dimension in a 3D, it may be that the red points. So if I convert this into two-dimensional and this is the z-axis, so it might happen that your red points are here and your blue points are here. But in two dimension, when you're just seeing x and y, it is appearing that it is on the same page and on the same circle. But if you see the third axis, it might happen that there is a particular partition that can be done. And this can be clearly separated. So how do you add this dimension? This is done by the use of kernels. So there's something called a RBF kernel. Don't go into too much mathematics, what is RBF kernel and all. Just understand this, that this is kind of a transformation. This is kind of a transformation you do to the data and add a kind of a different axis to the data so that the resultant data can be separated well. Do you understand this? I'll pause here.
In the 3 dimension, you get two linear lines, or again? It's just...
No, I'm just a single linear line only. Single linear line. I'm just. It's more of a plane, not a line. In 3 dimension, it will be a plane.
Plane.
So this transformation of the data, right, to create a new axis or a new dimension is very powerful of SVM. Okay, so this is why the SVMs sometimes they do not have too much importance. But if you just see a circular data, right, go ahead and do an SVM. Nothing will work here. No boosting, no neural network. No neural network might work, but linear regression and forest and trees will never work. That is for sure. So that's where that's where the SVM part comes in, right? So that's why it's very important to understand every model and its advantages and disadvantages, right? And okay, so now let's continue. So we have seen this. Okay. So okay, I'll just take your feedback and try to understand. Do you want to go into a deeper mathematics of this? I mean, because a lot of maths is involved and you don't need it. But what I'll do is, I think I'll show you something that is a little easy to understand. And okay, now I'll go very slowly on this. Try to understand this properly. Suppose there are two classes, this is positive and this is negative. Okay. Now I have a line which is kind of B naught. Sorry. So I say whenever a point comes, if it is less than 0, it falls here, and if it is greater than 0, it falls here. Okay. So these are the defined classes, and this is kind of the equation that I'm forming. Now, your objective function. Your objective function is basically that, so this is positive, this is positive, so product will be positive, but when it is negative, this is also negative, right? That's what we saw here. So when it is negative, this is also negative. When it is positive, this is also positive. So when I take the products of the two, it is always positive, right? And then you are saying that it should be greater than n. So what you're trying to say, when you're training this model, so this is basically the distance of the point from the line. Okay. So when you put, let's say this is the equation of the line. I will, after I explain this, I'll stop for questions. I know this is a little difficult to understand, but it's good to know. So whenever I put a point here, I basically get the distance of that point from this line. And I say that for all the training data, for all the training points, this distance should be greater than m. So what is m? So m is this part. So this distance should be greater than m. This distance should be greater than m, because I said that m is the shortest distance that the point the support vector is from the line. Similarly, this is also greater than m. All the distances should be greater than m. Okay. So this is your objective function. You want to have a line. Oh, sorry. This one is the objective function. You want to have a line wherein this is +1 or -1. This will take care of the sign. So forget the sign. Just concentrate on this part. If you put a point on an equation, that value will give the distance of that point from the line, and it should always be greater than equal to m. You want to have such a line here. So your function here is this. Now, does everyone understand this part? I'll pause here. Does everyone understand? If it is not clear, tell me. But you need to have this clear, because this is basics of SVM. Okay, that's great. Everyone is clear. Vasant, is it clear for you? Krishna? Okay. Okay. Well, person is asking, can you repeat what is M? Okay. Fair question. So M is the distance between this particular point to the line, and we have said that M is the least. I mean, beyond M there should not be any point, right? So what we have said is we want to have a point here, want to have a point here, and this should be M, this should be M. So there cannot be a point that should go below here. So M is the least distance that a point can be close to the line. Okay, so let's say M by 2 cannot, no point can be at a distance M by 2 from the line, because this is, I've chosen that this is the minimum distance that the point should have from the line. That's why I'm saying the margins, the line should have a proper good margin. So this is the margin, right? So the line should have M here distance here and M distance here. So all the points should be beyond those. So that's why the distance between the point and the line should be greater than M. Okay, got it. But as we saw that nature is not so kind to you that they will always give you a very clearly separated data set and you just draw a line here. Listen, you just had a question. I could not see. Can you just speak on the microphone so that I'm able to understand? I didn't see your question.
Shubhdeep,
Yeah.
are you able to hear me?
Yeah.
Yeah, actually, in future we may get the least point, right, again from the lane.
Yeah.
From the perpendicular lane.
Correct.
So again, that we need to change that M, right?
Correct. Right. So if you take that point into training, then the line will change. If you take that point and just as to or for a testing purpose, for example, if you just want to predict for that point will be predicted. But for training purpose, if you add that line, you're correct. That support vector will change.
Okay. Thanks.
Yeah. So as we said that, it's not very likely that you will always have such kind of data that is linearly separable, right? You might have some points here, some points here. Okay. How do you deal with that? So if you have such kind of points, then you'll not be able to have anything linear that can separate, right? You have to have some curves, or not even possible sometimes, unless you do that kernel approach. Okay, so what do you do in that case is you allow the line to be a little relaxed. You say, don't worry, you try to fit this, but have some leverage. Let some points go out of place. So for example, what I've right now said it is that your line is like this, and your points are, so your minimum this is M, and your minimum this is M. So what I've said is that each and every point should be greater than M. But what if some points are here, and what if some points are here? So you say to the line, don't worry, have some leverage, have some leeway here, not leverage, sorry, have some leeway here, that even if you misclassify some points, it's okay for me. Even if you don't have perfectly fit all the points, it's okay. So what you do is you introduce something called as an error. So error is basically, so for example, you keep a check on the total misclassification you want to have in the data. Okay, but for example, let's say take an example. Let's say M is 5. Okay, and I take sigma of error, it should be less than 9. Okay, so in some cases I can take EI as 6. So it means, what is this, minus 25, right? So you can take misclassify a point. So for example, if I'm trying to classify this, not classify this, I can say that even a blue point, which is kind of 25 distance on the other side, that can also be taken. Okay, if a blue point here is positive, a blue point here is a negative. So it allowing the function to take this into consideration. That, okay, let me explain again. You have this, your blue points are here, your red points are here, but there are some red points here and there are some blue points here. Okay, these are good, these points are good, no problem with them. They are, reds are on the red side, that's why they are positive. Blue is on the blue side, that's why on the positive. But what about these points? So these points are on the wrong side of the line. So you tell, no problem, you can go, I can have this much of leverage. Total error over all the 10, I mean all the data sets can be, let's say, less than 10. So you say, okay, that means, so if your m is equal to 5, so 5 1 minus 10, so that is minus 45. So even a point which is on the wrong side of the line with a distance of 45 from the line can be taken into consideration. Okay, so even let's say again, I find out, let's say this is 20 and I found another point which is, let's say, 11 from, not 11, I already taken 10, let's say I just have 7. So 7, so m is 5, so 5 1 minus 7 minus 30. A point, let's say here, which is wrong side of the line, a 30 distance from the wrong side of, on the wrong side of the line, can be taken into consideration. So this is the leverage you want. So total error should be less than a particular value. This value is user fed. This value is user fed. Okay, so this depends upon, so it's the same thing again, it's the same thing. You want to hugely overfit, you want to try to fit all the points, or you say, no problem, I can have some error and not fit all the points. Okay, so does everyone understand here? It's okay if you don't understand, this is a little difficult concept. Ask me questions if you have any.
Is there any real example like to understand this one?
Yeah.
Sudeep?
I'll
Like our blood pressure counts and like that.
So real example as in, you can use this model to fit a data,
Because it's
but it will not, I mean, I don't have the visualization right now. Maybe next class I can show you the visualization of how, it will not show you visualization dynamically. Let me see if I can find it on the internet, if there's some visualization that is dynamic in nature. But most of the images are like what I have already shown you. So it's a little difficult to understand, I agree, but just think over it a little more, what it is trying to do, why are we introducing this error part, why, what if I don't introduce the error part, what will happen? Just try to think over. We'll come back to these mathematical equations, to, if we can re-understand this. But
okay. Yeah, no problem.
nevertheless, it's not necessary that you have to understand this to understand the model. The model is basically what I've told. It's kind of a linear, it's kind of a partition between the positive or the negative class. Okay, and there can be multiple partitions as well. Okay, so it's kind of what it is doing as a partition. And so In random forest, we saw that the partitions are always perpendicular to the axis. Here, the partitions can be anywhere, right? So partition can be like this, it can be like this, it can be like a plane. So any partition will work. Okay, so that's how your SVM works. Okay, I will go back to this. Let's take a break of, let's say, 2-3 minutes. And if you have,
Quick question, sorry.
yeah,
Hello?
yeah,
Yeah. So the error, this thing, right? You're mentioning about the error, like positive point coming into the negative area, all
correct,
that, right?
correct.
So how are you defining this positive and negative? Is it some kind of a future that you're telling? Okay, if it falls all, if this is the future, then it's positive. This is the future, it is negative.
No, 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 no. Positive and negative, I've said that there are two classes. For example, yes or no. I've just denoted them as positive, negative.
Oh, okay, got it, got it. Okay.
Okay. So we're just trying to separate two classes, positive on the other side and the negative on the other side.
Okay.
Sunil, no questions from you? Okay. Okay, so let's take a 2-3 minute break and we'll come back, regroup. Okay, I'm back. So I'll not go into too much depth of all these. There's too much maths involved. Um, so I've already explained you all these things. Hard margin versus soft margins. This is the kernel that I was talking about, right? You can change the dimension. You can do a transformation. So Sunil, you're saying like how does transformation help when we are trying to play with the data? So this is how a very good example of how the transformation is kind of changing the way you are classifying the data. So you see the original input space can always be mapped to some higher dimensional feature space where the training set is separable, right? So in your two dimensional, your circular data is not, you cannot separate, right? But when you take it to the another dimension, add another dimension to it, you can easily separate it with a plane. Okay, so too many things that are there for So let's see the properties. If anyone wants to understand the maths, I'm open to it. I can explain you, but I mean, so okay, let's take a quick vote. Do you want to understand the maths, or should we take it later? What do you want? Give me your feedback. Okay, so I think majority of people are saying that it's not needed. So then let's talk about. Okay, Vasan, is that helpful in future? No, I would not say that they are much helpful because one, SVM is not very widely used. You cannot use that more. I mean, most of the data sets you will not use SVM. And the second thing is that whenever you are trying to implement the model, nothing of this is required. You just have to understand which kernel to fit and what parameter to put. So it's not necessary to understand the maths, but we'll see when we kind of fit the model what is required. So it's not required. Just so let's focus on the properties. So flexibility in choosing a similarity function, sparseness of solution when dealing with large data sets. So uh, if your data set is too sparse, right? So it works very good. Ability to handle large feature spaces. This is one very important. So in biology or in medical, you might have a lot of parameters. So for example, there will be parameters about your blood pressure, parameters about your heart, parameters about your intestine, your pancreas, anything, right? So there can be 200 or 300 features. But how many patients do you take for trials? So for example, if you're testing a cancer drug, you'll have a lot of parameters that you are going to record. But let's say how many patients do you have in the cancer trial? Let's say 1,000 or 2,000. So your n is to p. So we call it as n to when n by p. So n is the number of data points and p is the number of features. This tends to be one, or even sometimes even less than one, when your number of features are much more than the data set. So in that case, right? In that case, the SVM helps. So to answer every one of your question, right, that why you want to understand all the models. So this is why you want to understand every model, because every model works very good at certain point and very bad at a certain point. So you need to know where it works good and where it works bad. So for example, I fit a model on a medical data. There were 180 data points, that is too less, right? 180 n data points, and I had, let's say, 50 or 60 features. So it's a very bad N to P ratio in terms of data analysis, right? I did a boosting, I got 86% accuracy. I did an SVM, I got 97% accuracy. So that's the difference. But on a similar thing, If I do kind of have a very huge data set of, let's say, 10,000 n, and let's say only I have 10 or 12 features, then if I do an SVM, it will be very bad. Okay, so you need to understand where your which model is helpful where. Okay, overfitting can be controlled by soft margin approach. So what we have already discussed, that you now try, when you introduce the error term, you now tend to have a soft margin, right? So you can allow some points to be here or allow some points to be here. Okay, so this is called a soft margin. A simple convex optimizer which is kind of okay, and this is not require nice map property. Feature selection, it also helps in feature selection. We'll see that how it helps in feature selection. So see, bioinformatics, protein classification, cancer classification, right? Here, in these cases, you don't have too much of data to deal with, but you have a lot of features. So that's why SVM works on these pretty good. Okay, so anyways, it's not required. So it's very sensitive to noise, as you said, that it depends on just only two support vectors or just 2 points. I move them here and there, and I'll end up in a completely different model. Okay, so okay, I've seen just two classes, right? So when we have a multi-class problem, we always have this one versus rest approach. So for example, you want to classify, there are three classes: high, medium, low. So first you want to classify high and take this as a total set. Then you want to classify medium and take this as total set. I mean medium versus high and low. Low versus high and medium. High versus medium low. So one versus all rest approach. This is applicable to all the multi-class algorithms, right? Every multi-class algorithm, be it logistic regression, be it the random forest, be it the boosting, will always deal with this. Okay. So we'll not see text categorization much. We'll discuss this in NLP. Okay. Now let's get back to the mod practical hands-on part. So any questions now? Okay. So I took the iris dataset and kind of did a train test split. Okay, so I took the test size as 0.3 and I took a train test split. And here I do a classification. So you do an svm.svc. So it is the support vector classifier. If it is a regression problem, then you do a svm.svr. That is a support vector regressor. Okay. You put the kernel. I'll just show you what are the kernels available. So this is a linear kernel. Uh, this is an RBF kernel. See how your boundaries are curved now. This is a polynomial degree 3 kernel. You see how your different kernels can classify your data better, right? So let me see if there's a list here. It's not there here. So these are the, see how so this is the linear kernel, this is your polynomial kernel, and this is your RBF kernel. How different kernels are helping you to classify the data. Do you see this? So this is how your SVMs are very powerful. Okay, it's not so. Normally, there are two or three kernels on. I mean, three kernels that are very famous. There are a little more also. I think there's an exponential also, but no need. These are the three kernels that you can use as a parameter. So when you do a grid search, you can have these kernels in your parameter and check which of the kernels are fitting the best. Okay, so the RBF kernel is kind of the adding dimension to the model, which we discussed. Like if you have a circular data, go with the RBF model. If you have a curved data which you think a polynomial can hit, do go with the polynomial kernel. So all the equations that we saw, those are basically depending on the kernels. So if you're a linear kernel, your equation will change, what we had as a b naught plus b1 plus x b1 x1 plus b2 x2. That's a linear kernel. If you have a polynomial kernel, then you have b naught plus b naught b1 x1 plus b naught b1 x1 square plus b2 x2 square, something like that. Okay, and this is the speciality of your SVM. So I have used the linear kernel. C is the error total. I remember that what I put, sigma of EI is less than C. So C is the error that you want to put. Available, I mean, how much error you can take as an user. So you do this, and the same thing what we did. Okay, now we'll go to this later. So you see how your point, this is 0.98. When we did a logistic regression, it was somewhere, I think 0.97. So it has improved just with a linear kernel. If I do a RBF kernel, let's see if it works here. It's kind of same only, 0.98 only. Let's see if it is a polynomial kernel can be done. It has a little bit worsened, right? So depending on the kernels, your performance get affected. So let's say I want to have, sorry, this is 0.9778. If I do a 0.3, it's not, this is changed, right? So right now you're trying to induce less error. That's why you're trying to overfit, and that's why your test, this thing is there. So if you do a 0, let me see if it takes 0. You don't want any error in the training data. It has to be some value. See, it has reduced so bad. This is 0.24. So you have tried to overfit the data, and that's why your testing has become worse. So guys, understand this. Does this make sense? So for SVM, you just need to understand three things: the kernel, and is whether it's a classification, so SVC or an SVR. Uh, Kernel, which kernel is RBF, linear and polynomial, and C is the error that you want to. If you don't want any error, like if you want to have very less error, then you will try to overfit, and that's where your testing will testing error will testing accuracy will go down, and if you want to have too less underfitting, you want to increase the C to as much as possible. Okay, so any questions now? Sunil, questions?
No, but today's session is really going very good.
Okay, it's okay for you? Okay, great. Nice to hear that. Okay, so the last thing that I want to show you here is we have already done the decision tree, but what I wanted to show here is how to do a grid search. Okay, so grid search is a function itself in Python. So as you can see, this is the grid search CV. So what you need? You need a model which will do fitting. You need the parameters on which the grid search will be done. You need a scoring on which your let's say the scoring performance will be checked, and you want a cross validation sets. So these are the 4 parameters that you need for a grid search. Okay, so homework for you guys is to do a grid search on the boosting model on Boston and check for the depth and the learning rate and come up with the best one. Okay, so it's very easy. Let me explain this function.
By then, what is the use of this grid search?
Okay, so grid search, as I've already told you, grid search is something for to obtain the best parameter of the model. So as you remember, we have all last time what we did is that we ran a loop to keep it simple for you guys. I just ran a loop and saw how for different parameters. I think which one we were doing. I don't remember the model. So I just ran a loop and for different parameters we were testing the best model, right? So for example, if someone tells you which is the most optimum depth of the tree for my model in my boosting, how will you say?
No, could you repeat once again?
So if
I think so. I think so. You did that when you were describing that sigmoid function.
Correct.
So
So
for loop, we were going one by one.
correct. So similarly, for example, in the boosting, right now what we have done is we have just kept the n estimators to 500, the max depth as 4, minimum sample split as 2, and learning rate as 0.001. Now, who has told you to keep these parameters? No one, right? You just kept it with your own intuition, or you just kept it randomly, right? So you don't want that. You want the model to come up with the best parameters possible, which is the best depth of the tree, which is the best number of trees that you want to keep, what is the minimum sample split, which is the best one, and what is the best learning rate, right? So the grid search,
Yes.
what will do is it will try to find out the best model for you on the basis of these parameters and come up with the best model possible. Understand that?
What do you mean by no? What do you mean by best model? Means out of these 8 or 10 algo which we learned.
No, not the algos. Within the tree, I told you, hyperparameters are there.
Okay.
Depth of the tree, the number of trees.
I got it.
How do you define the number of trees to be 500? Should it be 700? Should it be 200? Should it be 1000? How do you determine that? So, for example, if this, you see the graph here, you see after 100 the test, after 200 let's say the decrease is too slow, right? Now let's say after 700 it starts increasing. So 700 is the optimum point for the number of trees. So how do you come up with this? You cannot do every time plot and see, right? So that's where the grid search comes into picture. It does kind of a search on all the parameters and tells you which is the best model that is possible for your best model that should be implemented. Not the
Okay.
best algo. It's not saying whether logistic regression will come. I mean, logistic regression or a SVM or a boosting. It says within boosting, what is the number of trees you should keep. Okay.
Okay, that's great. We will do as an exercise.
Yeah, you do this exercise. I'll just explain you the grid search algorithm. I mean, algorithm is nothing there. I just explained you. Just
It,
understand.
it means Shubhadeep, once we will go through grid search, we will able to see L estate on the top, then RM on the second, like this.
No, 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 no. You are not getting the point. Is
I'm
uh,
not.
okay, okay. Just three. See here. Just see here. My screen. Um, so you just have a performance metric. The performance metric is a score that you want to put. This is the model, which model you want to put. So this is the split. This is the split, as in you're taking some bit in the testing part and some bit of the training part. So you have taken test size is 0.2. 0.2 means 20%. 20% of the data will be taken in testing and 80% will be kept for training. Now just see here. The model I've taken is a decision tree. The parameters I've kept is as max depth, and I'm checking the max depth from 1 to 11. Okay. Now I want to see at what max depth the tree is the best one. I mean, gives the best accuracy. Okay. So I do a grid search. Grid search CV estimator is the regressor that the model I put. Grid parameters is the depth which we have put here. Scoring function is the score function, that is the R square that we have put, and CV sets is the cross validation set that we have put as a testing. Okay, then you do a grid dot fit, and then you do a return grid dot best estimator. So what it will say here, you see, parameter max depth is 3 for the optimal model. Okay, so between 1 to 11, 3, if you keep max depth as 3, you get the best accuracy.
Yeah. So with now I got it. Basically, for a particular model, what are the parameters which will be give us the optimal value?
Perfect. Yes, that's what you want. For a particular model, what should be the parameters that will give the best model?
Yeah, that's great.
Okay. Okay, so we'll close with SVM also. So any questions now? Out of any, whatever we have done from the starting, any questions?
I have still one question. Is out of these 13, how to remove 5? By default, those are getting removed in last show. But I want to see the means out of rank 1, there were 10, but I need top 4 or 5.
So you've got it, no? Yeah, on the previous graph, you have got it, no? Top 5 if you want to take.
Yeah, so means, yeah, this graph was generated by FVM.
No, this graph was generated by boosting. This graph.
Okay, just so once again, boosting dot feature names. Yeah. Okay, got it. Yeah, thanks.
No, no. I mean, I didn't understand your question. You get
I'll
top 5, right?
no.
Yeah.
Yeah, this thing only I was looking. So I will write a separate program for this only variable importance.
Yeah, variable importance plot here it has come. Now, out of these 5, let's say you want to take the LSTAT, RM, dis, age, tax. Okay. You take these
Yes.
variables in the data set. That is the normal subsetting, right, of a data frame. From the data frame, you just take these columns and then refit the model.
Correct.
Got it, right?
Yeah, that's what I was looking for. Thank you.
Okay, no problem. Okay, any other questions? Anyone else? Give me a yes or no.
So,
Oh, yeah.
so Sudeep, Are these only algos which we need to learn in regression and classification,
No,
or are there any which we can take care in future?
there are many. There are many. So many, as in many modifications of these. But on the whole, so now next we'll do naive Bayes. After naive Bayes, I think you have almost learned all the models except for the deep learning, and but there can be variations of these. Okay, but overall, if you would see, you have touched all the models possible. But of course, there will be variations. You can take an ensemble of SVM and boosting. You can take, there's so many infinite possibilities are there. But that I'll tell you how to modify the other models later. But as a whole, these are the big models, big picture of modeling. Right now, next we will do naive Bayes. After that,
Okay.
everything will be done.
And after that, sometime we will go for clustering also.
Yeah. So clustering also is there for today's class. But clustering is unsupervised learning. This doesn't have anything related to
Yeah.
supervised learning. Anyways, is this clear to everyone? So now next we'll move on to naive Bayes. Okay. Okay. First we'll complete the naive Bayes. Okay. So coming to the naive Bayes algorithm. This is a probability based modeling approach. Okay. So we can do a spam classification, medical diagnosis, weather. So I mean anything will like. So okay. Now I told you guys to go through Bayes theorem. Did anyone go through the Bayes theorem? Okay, so I think um, I'll explain you guys here only. So what naive Bayes is trying to do, we want to predict the probability of y. Let's say you want to predict the probability of y being high given your x features. What is this given? Given means conditioned on these features. You have these features, you have a value for this. X equal to 5, x2 is equal to 2, xn is equal to let's say 10. given that these values are there, what is the probability of y to be high? Okay, so this probability can be, let's say, 0.7 or anything that can be. So we are always dealing with probabilities, right? So now naive Bayes is always a classifier. This is very important. Naive Bayes cannot be used for a regression problem because it is dealing with probabilities. Okay, so now let's see what is what here. So probability of high phi equal to high given x1 x2 xn is equal to probability of x1 xn given y into probability of y divided by probability of x1. Okay, now what does this mean? So you say the probability of y equal to high given my features x is equal to what is the probability of having these features given y equal to high, then multiplying by the probability of high. Forget the denominator. Do you understand this notion? So I am trying to say is probability. Okay, let me change to OneNote and I'll explain you. Okay, so probability y equal to high given x1 xn Suppose you have this data set, right, and you want to predict what is the probability of y equal to high when x1 is equal to 2 and x2 equal to 5. What you'll do is you'll see probability of x1 equal to 2, x2 equal to 5 given y equal to high into probability of y equal to high. Forget the denominator. Denominator we'll see later. So can anyone answer me what is the probability of x1 equal to 2 and x2 equal to 5 when y equal to high? So okay, can you answer me on the microphone because it's difficult for me to switch screens. We can have a discussion probably so that everyone understands.
So it will be 1 by 4.
Not exactly.
Not exactly. There are 2 high. Out of it 2. Yeah, 1 by 2 it should be because
Correct.
there are 2 high.
Excellent.
And we want 2 and 5.
Correct. Excellent. So you see your data, you see y is equal to high in two places, and x is equal to 2 and x1 is equal to 2 and x2 is equal to 5 occurs only in one place. So this will be 1 by 2. Into what is the probability of y equal to high?
1 by 2, 2 by 4 equal to 1 by 2
Excellent,
effectively.
excellent. So you get this. So denominator is basically probability of x1 equal to 2, x2 equal to 5, given y equal to high, into probability of y equal to high, plus probability of x1 equal to 2, x2 equal to 5, and given y is equal to low, into probability y equal to low. There's a lag, I think, on the screen, so just bear with me. So what is the overall probability of having x1 equal to 2 and x2 equal to 5? That is equal to probability of x1 equal to 2 and x2 equal to 5 given y equal to high into probability of y into equal to high, plus the same thing given y equal to low into probability of y equal to low. Now can you tell me the denominator? What is this part? This is the same part, right, on the numerator as well, what we have seen. Correct?
Yes.
Correct? So this is 1 by 4. And what is this on the right? What is the answer on the right? You guys there?
Yes. Just
Should not take too much time, right? What is the
I
probability?
think it is also 1 by 4.
another is given 1 by 4.
Okay. Do you see x1 equal to 2 and x2 equal to 5 and y equal to low? On the left side of the table, do you see anywhere that
Yeah. On right side again it will be 1 by 4.
no, what I'm saying is, what is the probability of x1 equal
Oh, I think it is 0.
correct
Yeah,
0, right?
yeah, because
You
yeah.
never see probability of
Yeah,
x1
because
equal to 2 and x2 equal to 5 as any occurrence when y equal to low. So this is 0.
Oh, so, yeah. 0.
right.
So what is 1 by 4 divided by 1 by 4? That is 1. Now if you see all this calculation leaving aside, if you just see on the table, what if given this data, what if someone asks you what is the probability of x1 equal to 2 and x2 equal to 5 and y equal to high? You'll never even think twice. It has only one occurrence, and that time y was high. It means on the basis of the probabilities, on the basis of the data, you'll always say that this is 1, right? Because you only have one occurrence, and that time y was high. Understand this? Guys, give me a yes or no so that I understand whether you are getting the. Okay, so how many data points are there? 4 data points are there, right? How many times 2 and 5 had occurred simultaneously?
Once.
Once.
Yeah.
Once.
Okay.
And what was the y status at that point of time?
Only high.
Only high. Excellent. So it means from the data, you can always say that whenever x1 is 2 and x2 is 5, y will be high, right? I don't have any other option.
Yes.
Correct. So this is how your knife base will work. Now, knife base. Okay, now knife base has a particular.
So Sudeep, this one is Sir, this one is not clear. Why it's not 1 by 2? Why it's 1? Because there are two occurrences of high for y.
Yeah.
Out of these two, there is only one occurrence of 2 and 5. Then why not 1 by 2?
Oh, what I'm trying to say
No,
is,
x1 and x2. x1 is 2, x2 is 5. How many occurrences were there?
I'm not saying what is the probability of y equal to high. I'm not asking you this. What am I asking you is probability of x1 equal to 2, x2 equal to 5, given y equal to high. What was this? What did you answer here? Your high was 2 times and this one occurred 1 time. But now, what I'm trying to say is,
Yes.
what is the probability of y equal to high given x1 equal to 2 and x2 equal to 5? How many occurrences of x1 equal to 2 and x2 equal to 5 you have?
That will be 1.
Correct.
Yeah, that's
And then what was the probability of high in that case? I mean, how many occurrences of y equal to high you have in that case?
only for 2 and 5 there is only 1.
Correct. That's what. So it's a definite thing. Whenever you're
Okay,
seeing
got
2
it.
and 5, your y equal to high is 100% 1.
Correct.
Correct? Awesome. So this is very easy when you have 4 data points and you just have 2 features. What if you have 1000 data points, or let's say 1 lakh data points, and you have 1000 features? Can you just look into the data and see all these things? No, right? It's not practically possible
No.
to see all these things. And that too, one thing you might have noticed, I've told you 2 and 5, these are classes. Okay. Now, what if I want to predict for 2.1 or 5.2? There's no particular cases in that case, right? So first, let us understand how how naive Bayes behaves when the features are categorical. So when the features are categorical, like how I stated here, like assume that these were categories 2, 5, 3, 5, 4, 6, and 7, 2. I easily could find out the probabilities concerning that. Okay, but what if there were numerics 2.1, 2.2, and now I want to predict for 2.3? Okay, so that is a different approach that you have to follow. We'll not see that right now. First, let us understand how when you have categorical features, what your naive Bayes helps. So a big assumption of naive Bayes is probability of x1 equal to 2 and x2 equal to 5 is equal to probability of given y equal to high is equal to probability of x1 equal given high into probability of x2 equal to 5 given y equal to high. So this is the assumption of independence. You say that my x1, okay, now basic formula of probability is x, and probability of x and y is equal to probability of x into probability of y if x and y are independent. Do you know this?
Yeah, you know.
Okay. So it means the assumption of naive Bayes is probability of x1 equal to 2 and comma x2 equal to 5 given probability y equal to high, given y equal to high is equal to probability of x1 equal to 2 given high into probability of x2 equal to 5 given y equal to high. So this is the independence assumption. Why this helps? Because when you have 1000 features, or let's say very high number of features, it is not practically feasible for anyone to go into the table and look into the probabilities of individual occurrences, right? So if there's an assumption that this should follow, that whenever I am doing a naive Bayes, all the features are assumed independent. Okay, they're assumed independent, and that's why we can multiply the probabilities of each of the features. Does this sound good? Is everyone comfortable with this?
Yeah.
Yeah. Yes. Yeah.
Okay.
So, Shubdeep, why do you want to see those values? Like
Sorry.
you have first row as 2, 5.
Correct.
So then why do you want to check the probability there? It means you have only one high for 2 and 5 value.
Okay. No, this was an
So you
example.
have
This was just an
only
example.
one occurrence.
So, for example,
So if you have one more row and with 2 and 3, x1 as 2 and x2 as 3 and
suppose
y as high.
no, suppose you want to predict now. So someone gives you 2 and 3. Now you gotta predict what will be my y. Will it be high and low? You don't have 2 and 3 in your data, right? So what you'll do, you'll say, what is my probability of y equal to high given x1 is 2, x2 equal to 3, right? So this will be probability of x1 equal to 2 given y equal to high, and probability of x2 equal to, okay, not 2 and 3, let's say 2 and 6. Okay. uh, okay, let me write it in a different. Okay, now you see, I give you 2 points, 2 and 6. Okay, and now I say I want a prediction. What is the probability that y equal to high? So what I do, I write the same formula: probability of x1 equal to 2, comma x2 equal to 6, given y equal to high, into p of y equal to high divided by this, the formula. Now I say that this is wherein the assumption of naive Bayes comes in. So I said probability of x1 equal to 2, given y equal to high, into probability of x2 equal to 6 given y equal to high, okay, into probability of y equal to high divided by probability of x1 equal to 2 into probability of x2 equal to 6. Is this fine? In both places I've used the naive Bayes assumption.
Yes, yeah. We have used yes, yeah.
Correct. Now what is
So
the
there
probability?
we have first,
What is the probability of
yeah.
x1 equal to 2 given y equal to high? Now let's go back to
I
the
think it's 2.
y equal to high is 2 occurrences. What is so this is 1 by 2, right?
Yes, yeah.
What is the probability of x2 equal to 6 and y equal to high? X2 equal to 6, y
1,
equal to high is 0, right? So this is 0.
0, yes, yeah.
So on top, this is also 0. Divided, I'm just writing the value so that you understand that. Into probability of high is 1 by 2. Divided by, what is the probability of x1 equal to 2? What is the probability of,
1 by 2.
no, I'm not saying conditioned on y equal to high. I'm saying what is the,
1 by 4.
awesome. So this is 1 by 4. Similarly, what is the probability of x2 equal to 6?
1 by 4.
Correct. So this is essentially 0, but you understand all the numbers, right?
Yes, yeah.
Okay. So everyone is clear with this?
Yes.
Okay, amazing.
Yeah.
Let's go back to the slides. So it's telling you the same things again and again. Okay. So leave these things. Okay, now we can see, let's see this. Okay, for example, you had this data where you are seeing outlook, the temperature, the humidity, the windy status, and whether they are going to come to play or not. So let's say someone asks you, what is the likelihood of children going to play? Equal to yes. Okay. Given, let's say, these parameters, it is sunny, it is cool, it is high, it is windy. Okay. Now let's find out. So we'll write slowly and we'll understand. So probability of play equal to yes, given sunny, cool, high, true, equal to probability of sunny given yes into probability of cool given yes. Okay, I'm running out of space. Let me write it here on the top. Probability of sunny given yes to probability of cool given yes into probability of high given yes into probability of true given yes. Okay, now see, when your play is yes, what is the probability of the outlook being sunny? So these are the possible outlooks, and these are the number of occurrences. Okay, now what is the probability of, understand this very slowly, what is the probability of the outlook being sunny when children came out to play? Just see this row, nothing else.
Two by 9.
Perfect. 2 by 9. What is the probability of the, let's say, just an example, what is the probability of this being overcast given yes? You already have the answer, 4 by 9, 3 by 9. Okay. Similarly for no, what will be it? 3 by 5, 0 by 5, 2 by 5. Understand?
Yes.
Okay. Similarly, what is the probability of temperature being cool given yes? So given yes, what is the probability the temperature is cool? See this.
3 by 9.
Perfect. 3 by 9. What is the probability of humidity being high given yes?
3 by 9.
Perfect. So now I think you guys know that the answer is here. So,
It's
and
already written there.
yeah. So just put into perspective, these are the values: 2 by 9, 3 by 9, 3 by, sorry. Okay, this is also 3 by 9, 3 by 9. And what is this 9 by 14? So what is, if we go to this formula, this is, and then we also have the probability of play equal to yes. Remember, these were the x given y, and then there was a probability of y also, right?
Yeah.
Yes. Yes.
This was there, right?
Only play.
So similarly, what is the probability of play equal to yes? Play equal to yes is 9 divided by 14, 9 by 14. right? So this is the probability of 0.0053, and then likelihood of no is 0.0026. So what is the answer then? What is the probability? I mean, whether you say people will come out to play or not, what will be your answer? What will be the answer? And the answer is already on the slide. The prediction.
It will be no.
Yeah, because the
because
probability of
0.02
yeah is higher than probability of yes.
yes.
Okay. Understood? I think this is very clear, right? We have gone through the example.
So this naive bias is mainly for binary classification.
I think binary classification. I mean, yes or no, is it?
Yes.
No,
Yeah.
no. Multi-class also
Zero
can be. Or multi-class also can be.
multi-class. Okay.
Okay, so now we have seen how we can predict a binary class given the features are categorical. Why categorical? Because, for example, sunny was a categorical feature. I mean, temperature was a categorical. Overcast was a categorical feature. Overcast had just 3 values. Sunny, uh, what was it? Sunny, overcast. Sorry, outlook. Outlook was a categorical feature with sunny, overcast, and rainy. Just 3 possible values. What if you have a continuous value? Okay, so what if you have continuous values in the features? Does that mean I cannot apply naive Bayes? No, that is not the that is not the case. What happens in that case is that you assume that each of the feature will follow a normal distribution. For example, let's say I have the height and weight. Let's say height is 200 centimeters, 180, 190, 250, 250 is too high, sorry, 160, 165. Similarly, weight is 95, 90, 75, 60, 62. You want to predict whether it is a male, female, female, male, female, right? So based on the height and weight, you want to predict the. So what you assume is, you assume now you cannot have the occurrences. These are continuous variables, right? So you don't have a categorical feature. So what you assume is that your height and weight will follow a normal distribution. So height is following a normal distribution with a mean. Let's say what is the mean here? Let's say the mean is 170 centimeter, and let's say the standard deviation is 10. So height will follow a normal distribution of mean calculated from here, and a standard deviation again calculated from here, and it will follow a normal distribution. So if I have a normal distribution, I have the mean. Now if a new number comes up, let's say 179, can I calculate the probability of 179 from a normal distribution where the mean and standard deviation is given? Remember our first class, the Z values, where we were saying the marks of the student. If the principal asks you what is the probability of this child being greater than 39 marks out of 40, remember that? Same thing. What is the probability of a new person having a height 179 centimeter if your height distribution is a normal distribution with the mean this and standard deviation this? So from the normal distribution you get a probability. Similarly, weight will follow a normal distribution with a different mean and different standard deviation. And you tell that the weight of this same person is, let's say, 76. Now, what is the probability of 76 coming from a male, and what is the probability of 179 centimeter coming from a male? Male. And then accordingly, you get the probability that the person is a male. And similarly, from a female, you get the probability that the person is a female. Do you understand this? Or I think this is not clear, right?
Yeah, this is the same bell curve you described
Correct.
in the first or second session.
Correct. Okay. So basically, you do this. Now, there are a lot of slides in this, right? Okay, now I think we have already explained this. So, for example, if your if this temperature is continuous variable, your humidity is a continuous variable, then what is the mean, what is the standard deviation, what is the mean, what is the standard deviation? Rest is categorical. So you calculate the mean, you calculate the standard deviation. This is the function of the normal distribution. So you feed in your new variable. This is the mean. This is your standard deviation. And this is also your standard deviation. From this equation, you get the probability. So if a variable is, let's say, I want to find out for 85. So it is 85. So 85 you feed into this equation. The mean is there. And accordingly, the probabilities will come. So what is the probability of temperature equal to 66 given yes? You feed in this. Okay. You calculate this, and the same way you get the answer. These we have already seen. These came from the equation. So this is 0.0340. And similarly, if you do for humidity, you will come to get something as 0.0221, and then you get the answers. Okay, is it okay?
Yeah.
Okay, great. Knife base is often a good choice if you don't have much training data. Okay, so I'll not go into so much of these things. These are not required. We have all seen this, right? For sensitivity confusion matrix, we have discussed this sensitivity these things. So, okay. So there's something called an ROC curve for a classification. So as we said that there's an F score, which is the harmonic mean of sensitivity and specificity. There's something called a ROC curve and the area under the curve, AUC. So this is called receiver operating characteristics. Just the name, nothing fancy about it. Just the sensitivity versus 1 minus specificity is the curve plot. There's something called an area of the curve, right? So an area of the curve will be equal to 1 if it is something like this, right? So if you just analyze your, just go home and analyze this, AUC equal to 1 is the best possible scenario. And I'll ask this question next class. Why is AUC equal to 1 the best scenario? Otherwise, a AUC like this is 50%. It means it's kind of you're 50% good in fitting the model. Like your R square, you are 50%. If it is 0.5, it means you are around 50%. So AUC, if it is around 0.5, you'll say you'll around 50% good in fitting the model. Okay. So and if you have AUC equal to 1, then that is the best case scenario. Okay. So we have already discussed cross validation. We have done all these things. Okay. The task of test classification, this I will discuss later because this is a little difficult, and since you just have got knife base ingested, I don't want you to get too much complexity of knife base. So this we'll discuss when we do the natural language processing class. Okay. Now let's move on to clustering. Clustering is a very simple uh, algorithm and very loved algorithm. It is very easy to implement. Okay, so we'll see what is the uh, so how much time we have. We have around 20 minutes. Okay, so now any doubts still here, because clustering is a different chapter, so any doubts still here?
So this naive, what you have mentioned, this is used for the unsupervised learning, or can be used for both supervised and
No,
unsupervised?
naive base is for supervised learning. That's why,
Supervised.
because probability of y equal to high, given when we are doing on the right side, probability of x given y equal to high. So you need to know when your y was high, right? So you also always have to have a supervised thing for naive base. But naive base is only used for classification and not for regression.
Okay.
Okay, so
So this naive base is means looks similar to that decision tree, means, isn't it?
not exactly.
Decision type model. We worked on one example.
Not exactly. It's not decision tree. It works on the concept of probabilities, but it's not decision tree. Decision tree is
Okay.
kind of taking partitions and all. This is not the background behind decision tree is Gini index that deals with probabilities, but it is not similar to naive base. Okay. Okay. Now,
Okay. So just sorry, just one last question.
yeah, sure, no problem.
Again, I want to analyze that Boston set now again, because now we have learned all the algorithms.
Okay.
So again, I remember your steps which told you on that day.
Correct.
So first I have the data sets, and then now I can decide, okay, these are the top 4 or 5. How many I have to take, I can decide that.
Correct.
So that is one thing now I'm able to do out of 13, which one I want to. Then I know cross validations, how many fold I have to do that.
Mm-hmm.
And then what do I try with different model with their variables, I mean parameters, and see which one fits best, or is there some other way around?
No, there's.
I mean to say, okay, my straight question is that this Boston set my manager has given to me.
Okay.
Now I have to predict something. I have to say how much accuracy. That will be the first question.
Mm-hmm.
The second question will be some visualization part. So can give the PPT based on this one.
Okay.
And why you have removed this one, why you have not removed this one. What can be the extra story that can come around?
Okay. So accuracy part, I think we have addressed all through these weeks. What we have seen is that you move from model 1 to model 2 to model 3, okay, based on your accuracy. So whatever accuracy you are getting, if this is lesser than the accuracy here, this is lesser than accuracy here, right? So this can be a linear regression. This can be a random forest. This can be a boosting. You always start with a linear regression, then go on to a random forest, then go on to a boosting. Prior to do a variable importance plot. So variable importance plot is connected to these two methods. Linear regression is not very effective in giving you the variable importance because it just gives you coefficient. So once you get the important variables, you feed back these important variables to the model and then get a better accuracy. Okay. Now, once you have this model ready, okay, now we just have the variables. After that, then there is a step called cross validation and grid search, which will give you the hyperparameters. Which is the max depth, entries, and all. After you get the optimal hyperparameters, you kind of feed back this to your model, and then you get the best accuracy. Correct? Now, further to improve this, you need to do a feature engineering, which is not in the scope of our course. Okay, but this is more of related to business knowledge. Feature engineering can also come with the transformations. So you transform the data, you do a feature engineering, and this you feed back to your model. You again do a cross validation and grid search, and then you get the best accuracy. So this is kind of the loop that you need to follow. But since feature engineering is not in the scope of our course, we will see which is the best model. Then after we select the model, we see the parameters, hyperparameters, and after we see the hyperparameters, we kind of tell the best accuracy possible. Now, data science like R and Python, or let's say Python, what we have done. Python is not related to visualization. Okay, this is not a visualization tool. The only thing you can see is the summary statistics or how your variables are moving. Okay, what is so if your boss asks you that give me insights about uh, let's say what is your insight that has come up. So let's say you're on the same Boston house data set. So if you work in a real estate company and your boss asks me what is the driving factor, so you'll say that LSTAT is the driving factor. Now your boss may ask, okay, tell me if I have to increase my price by 10%, then if I want my customers to pay me 10% more than what it is paying, which variable should I reduce? Okay, which variable should I reduce to gain that 10% increase? Okay, so this is called a scenario building. Scenario building is basically, for example, your LSTAT, you see the correlation of LSTAT with the price. Okay, if it is positive, it means I think it was opposite. Yeah, it was negative correlation because LSTAT is the number of, yeah, it's a negative.
Yes.
So if you decrease your LSTAT, so let's say if you decrease, if you say I input LSTAT to 0.6, keeping all the other variables constant, what will be the price predicted? Then you say, okay, now let's say if I decrease my LSTAT to 0.3, what would be the price? That is your analyze. That is your scenario generation. That what if scenario? What if I do this? What will be the price change for other variables keeping constant? Okay. Then he says, okay, LSTAT I cannot do much more because that's the neighborhood. What if I can crime rate I cannot control much. So what if I can change the number of rooms? So you'll say, okay, if you change the number of rooms from 2 to 3, the consumers are willing to pay this much increase of price. So let's say if you have all the variables constant and do not change anything on the other variables, just keep the price from 2 to 3, sorry, the room number of rooms from increase from 2 to 3, and then predict for the same data point, then what will the price change? Okay, so for example, if you take the random data point where the number of rooms were 2, now in the same data point, all the features you keep same features, just the number of rooms you increase from 2 to 3, and then say, okay, my price has changed with 10%. Now you go back to your boss, you say that, see, if I change 1 unit of rooms, there I can expect a 10% increase of price. So can we do a cost benefit analysis saying that what is the additional cost for us to make another room in an apartment, and I mean for future houses, and my customers will be willing to pay me this much. So this is the insights or the things you can get out of your predictive model. But the visualization part is different. Visualization is more of the diagnostics of what are the variable, what is the variable mean, variance, deviation. Uh, when you have to skewed data, you need to transform that. So that's where your visualization comes into picture. So this is what your data science will look like overall. Okay.
Yeah, that's a great story that I was looking for. So basically 2-3 points you told me which are very new for me. So inside or you can say this, what was the term you used? If I decrease L state by something delta or increase delta, what will be the effect?
Scenario building, inside generation.
Data building or business insight.
Yeah.
Or scenario building basically.
Scenario building, yeah.
So yeah. So if I have to increase delta in a particular field, then how will I proceed? I will just go in Pendage, and for a particular column, I will add delta to every, or is there some other way around to do this?
No.
If that is a very basic thing I can do, but is there some better way to do in Python?
No, I mean,
learning?
You can change a column and increase by 10% to anything, right? That's see that those things you have to find out. What is the better way to handle your data, or manipulate your data? There are many ways you can do a data frame subsetting. You can manipulate the variables. There are many ways, but what is the most efficient way, that you have to find out according to it will gain slowly with practice. It's not that today only people understand, okay, this is how you should do everything, right? Slowly, when you start coding and all, you'll start to understand how you can feed in new data, how your so feeding new data is very easy, right? We have already seen that if there's a new point, we just convert that into a data frame and feed that to our model, right? So that's there. But apart from that, there are many ways where you can do a data manipulation. Okay. So
and
yeah.
Sorry.
Okay.
For plotting
I have to finish the
math plot. Sorry, yeah, please go ahead.
Yeah. So because we just have 7 or 8 minutes. So clustering is basically unsupervised learning. Okay. So what is an unsupervised learning? We have already seen that when your y is not there, okay, so I don't have a response associated to every data point, right? So how does this help? So we have already seen clustering, I think, a little bit, but to be a little more detailed. So for example, if you have somewhat like data points are, this is a scatter plot. Okay, now you say this is the height and this is your weight. Now you say that I need to find out who are the males and females, but you forgot to annotate the data when you were collecting. So you do a clustering and you kind of come up with groups. Okay, so these groups, now you know that you are trying to find a male and this is female, and you kind of are trying to find a male. But there are many cases where you don't know what you're trying to. I think there's a lag on the screen. We'll see the drawing in about some time. Hello, 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 hello.
Yeah, we can hear you now.
Mr. Budit,
Yeah,
we lost you.
yeah. I think there's a problem with the connection. Anyways, so I think even my iPad got disconnected. Give me a 2 minutes. I'll just connect. Okay, by the time it connects, I'll just continue with what I was saying. So in unsupervised learning, you don't have the whys, and yeah, we'll just wrap up very fast. I think we can continue the clustering next time. So you don't have the whys in picture. You have the data scatter plot of it, and you're trying to figure out that what will be the kind of groups that can be coming out of the data, and see a proper segregation of the groups. Okay, so this kind of doesn't help very much because it's unsupervised learning. The insights are up, left to the user or the modeler to understand. But the thing is that there are certain sometimes there's no. So for example, it can also help in insight generation, right? So I'll give you an example how clustering will help you in insight generation, but it's not very handy. It's kind of doesn't make much sense. So it's basically the same algorithm or the same type wherein we saw the k nearest neighbors. It is kind of uh, calculating the distance of each of the points, and it's kind of assigning the same cluster to the points which are closer to my. So what it does, it's essentially, I'll tell about the algorithm first. So what it does is, just hold on. Let me try to connect my iPad if I can, very fast. Okay, so we are online. Let me share. Okay, so I'll do this very fast and we can continue on the next class. What essentially it does is it kind of assigns. So how do we start creating this cluster? Let's see, we have the same data and the clusters are not there. Okay, let's see, we have the same data. Now what it does is you tell how many clusters you need. Okay, so that is kind of a user input. So you say that you need around 3 clusters. Okay, so what it will do, it will randomly assign 3 points randomly. Okay, I'm sorry, it does it out of the data points only, so it doesn't go out of the data. It will randomly assign 3 points. Okay, random assignment. So what it does is it calculates each of the points distance from this point. And so for example, if this point is closer to this point, it goes into this cluster. This point is closer to this point, it goes this cluster. This point is goes to this point. Okay, so like this the clusters assignment start. Now this group is assigned out with whatever points come inside. They calculate a new centroid or a new mean, and then this cluster will have a new mean, and then again this cluster will have a new mean. Similarly, this cluster will have a new mean, and then again the same procedure is done, and again a new cluster will be formed, because now the distances are calculated from this point, from this point, from this point. And similarly, so new clusters, a new center point is this, so your clusters will be built around this. You build around this, so whichever point, so for example, if a new point is there, if this point is closer to this mean, it falls into this cluster. If this closer to this mean, it falls into this cluster. Okay, or if it is closer to this, it falls into this cluster. So like this it keeps on reiterating the process, right? And it kind of goes like this. So when will the algorithm stop? When the t minus 1, I mean the previous center, is equal to the tth center. Okay, so what I told, that every time the first cluster center assignment is random, right? So I have a random assignment. Next, so after this assignment is done, we have kind of the clusters. Next, what will happen is this cluster will have a new center because new points came in, and then again a cluster will be formed. This cluster will have a new center because new points came in, and it will have a new center. Similarly for this. So next, again new points came into this cluster, I'll have a new center, and again a cluster will be formed. So this is an iterative process, and it will stop when your previous one cluster and the tth cluster, the cluster centers do not move at all. Okay, so we'll continue this in next class. Just and the distance measure is the same that is used in k nearest neighbors, right? What we learned is k nearest neighbors. What was the distance? X1 minus x2 whole square. Sorry, x1 minus. So if this coordinate is 2, 5, and this coordinate is 3, 7. So basically 2 minus 3 whole square plus 5 minus 7 whole square. So this is a distance measure under root of this. We'll continue this in next class. But if you have any questions for today, you can ask me. Any questions?
No question from my side, sorry, but really today's session was best.
Okay, thank you so much. Thank you. Okay, so we close today for today now. Then, thank you so much for joining.
Yeah, okay. Good night and see you.
Yeah, let's meet next week. Thank you. Good night, everyone. Bye.